It is part of a larger project to use Keras to detect objects using the YOLOv3 model. Here are the steps involved in using this specific code. 1. Using the makeYOLOv3 model function, we define the first model variable. In a second now, in Keras, makeYOLOv3 model creates and returns a YOLOv3 model. The third thing, training and predicting the YOLOv3 model will be based on this model variable. 4. YOLOv3 models can be built based on a YOLOv3 architecture by loading pre-trained weights into the makeYOLOv3 model function. In addition, it is possible to train the model on a specific dataset or use it to make predictions as new images are acquired. The sixth point. As a result of this code, we can easily instantiate a YOLOv3 model in Keras, which can then be used for object detection. It uses the Keras YOLOv3 You Only Look Once algorithm for object detection. We import the WeightReader class from the WeightReader module to load the model weights. On a large dataset of images, these weights represent the learned parameters of the model. Second, we create an instance of the WeightReader class, passing in the path to the weights file. As the name implies, this class loads weights from a file and stores them in a format that can be used by the model. Next, the WeightReader is used to retrieve the model architecture and create a model graph. An object detection neural network can be represented by this graph, which shows the layers and connections between those layers. The final line of code creates an object from the Keras YOLOv3 model class, passing in the model graph. By using the YOLOv3 algorithm, the model object can be used to detect and label different objects in new images. The code snippet above sets up YOLOv3's weights and architecture to perform object detection using Keras. With the WeightReader class, the weights of the YOLOv3 model are set. A WeightReader class is used to load weight files into a model. A weight-based model is used to update parameters and improve performance. In order for the model to make accurate predictions, the weights must be loaded in advance. As a result, this code ensures that the model is configured properly with the necessary weights during object detection. With this line of code, the Keras model that was trained and created in the previous steps is saved. With Keras, we can save a model to a specified file location using the .save function. .h5 is the file name for the model here. Models can be loaded again and used for predictions or further training after being saved. In Keras, this code performs object detection using YOLOv3. As part of the training process, the weights and configuration information will be saved in the model that is saved in this line. Objects can be detected in new images and videos using this method. AH5 file is imported and loaded in the first line. Pre-trained model that has already been trained on large datasets and is able to detect objects. The loaded model is then assigned to a variable called model. Our code uses this pre-trained YOLOv3 model for object detection tasks without having to train the model ourselves. With this code snippet, we can load an image and convert it into a NumPy array of 416 by 416 pixels. In deep learning models, the pixels of an image are scaled to have values between 0 and 1. It prepares an image for input into a YOLOv3 object detection model, as it requires certain input sizes and pixel values. The image is now ready for object detection by the YOLOv3 model after following these steps. As part of the Keras object detection code, this code fragment uses YOLOv3. Image is an image retrieved from the file zebra.jp and stored in a variable called image. Using loadImg, width and height of the image are obtained, and they are then assigned to the variables width and height. YOLOv3 requires a specific size of the input image to be accurate, so this information is crucial. After the image is resized and prepared for detection, it is resized according to the width and height of the image. This code loads an image and retrieves its width and height for use in object detection on Keras with YOLOv3. Here's a code for preparing an image for object detection in Keras using a YOLOv3 model. A function called loadImagePixels is defined in the first line of code, which accepts a file name and a desired shape. Using Keras's loadImg function, the code gets the original width and height of the image. A new image is loaded with the target size argument with the desired shape. With the img2array function, we convert the image into a NumPy array. A scale of 0, 1 is then applied to the pixel values of the image by dividing by 255.0. As a final step, we add an additional dimension to the image using the expand dims function, so that we can use it as a single sample for YOLOv3. The function then returns the preprocessed image along with its original width and height. It resizes the image, converts it to a NumPy array, and rescales the pixel values for object detection using YOLOv3. This model's input shape is defined by the first line of code, which is 416 pixels in height and width. We then define a photo file name, in this case zebra.jpg. A third line loads and prepares the image by calling the load_image_pixels function and passing in the expected input shape and the photo file name. It is likely that load_image_pixels loads the image from the file name specified and resizes it based on the expected input shape. In the following step, the resized image and the new width and height are assigned to the variables image, image_w, and image_h respectively. As an introduction, in the first line of code, we call the model.predict function on an image, which is most likely an input image for object detection. For predicting the image, this function runs it through a pre-trained YOLOv3 model. Here is 2. In order to analyze and process y hat, it is assigned to a variable, a, reconciliation. The next line of code uses a for loop to iterate through the arrays in y hat, which is likely an array list. The fourth parameter, each array in the list has its shape printed out using the .shape method, in 5. As a result of this step, we could understand the dimensions of the output of YOLOv3 and use this information in further processing or analyzing the predicted objects. As mentioned previously, using the shape of each array, we can get a better understanding of the results of object detection by seeing how many elements each array has and its dimensions. The seventh key. This code snippet enables us to make predictions on an input image using a pre-trained YOLOv3 model and generate the predicted array shapes for further analysis. As a demonstration, this code snippet shows how to apply YOLOv3 to Keras, a popular object detection algorithm. The first step is to import the necessary libraries. Next, an image is loaded and prepared for prediction by a function. In addition to resizing and scaling the pixels, an input shape is created for the model. Then, the YOLOv3 model is loaded and the expected input shape is determined. In the following step, an image is loaded and prepared for prediction using the previously defined function. A prediction is made using the model and the output shape is printed afterward. Data related to the detected objects in the image will be output as a list of arrays including their coordinates and the class corresponding to them. Using Keras, this code snippet performs object detection using the YOLOv3 algorithm. As soon as the code is executed, anchor boxes will be defined, which will be used to detect objects in an image. Objects in an image are identified and sized using anchor boxes. A probability threshold is then defined for each detected object in the code. Objects detected below this threshold are filtered out. Following this, a loop iterates through the outputs of each anchor box in the network y hat. By passing the anchor box dimensions, probability threshold, and input height and width to the decode netout function, the network results are decoded. Afterward, the decoding results are added to the list of boxes. After that, we correct the bounding boxes' sizes to match the input image. Input images are multiplied by their width and height to determine the bounding boxes. As a result, this code takes in an input image and uses the YOLOv3 algorithm and predefined anchor boxes to detect objects and that return their coordinates and dimensions. YOLOv3 code takes bounding boxes, YOLOv3 input image, and height and width of the original image. In addition, the bounding box correction factor is calculated according to the difference in size between the original image and the input image. For each bounding box, this correction factor makes sure the coordinates of the bounding box are adjusted to the correct size. In order to detect objects accurately, the YOLOv3 model requires input images to be a specific size. This code snippet is part of a larger code snippet for performing object detection with Keras using the YOLOv3 architecture. A list of boxes and a threshold value are passed to the function doNMS. In an image, the boxes represent the predicted bounding boxes. It uses a non-maximal suppression algorithm to filter out duplicate or redundant bounding boxes. To be considered duplicates, two boxes must overlap by 0.5 in order to be considered identical. Each detected object is bound in such a way that only the most accurate and relevant bounding boxes are retained. From YOLOv3's list of bounding boxes, labels, and scores, this code is used to get all of the results above a particular threshold. 3 parameters are required: bounding boxes, labels, and threshold. Each box, label, and score above the specified threshold is stored using these parameters. Firstly, the function creates 3 empty lists: vboxes, vlabels, and vscores, which will be used to store the filtered results. In the loop, it checks if a certain label's score exceeds the threshold by checking each box in the list. Boxes, labels, and scores are added if they are applicable. This function returns 3 lists that can be processed further or visualized. In addition to filtering and selecting only the relevant results, this code can also be used when dealing with a large number of bounding boxes and labels. First, the code snippet creates a list of labels for different objects, including a person, car, and bicycle. In order to get the boxes, the code calls a function called getBoxes with 3 parameters: boxes, labels, and class threshold. A detection model likely outputs the coordinates of bounding boxes in the boxes parameter. Using the labels parameter, we define a list of objects with higher confidence scores to be filtered out of the detected ones. 3 variables are created as a result of the getBoxes function: vboxes, vlabels, and vscores. In addition to containing information about the detected objects, these variables also likely contain information about their coordinates, label, and confidence level. This code gets the details of the detected objects from variables and stores them for further processing or analysis. As you can see from this code snippet, there are no specific details and functionalities of the getBoxes function. Code snippet for iterating over bounding boxes with corresponding scores and labels. A for loop is used to loop through the list of bounding boxes, and the len function is used to get the list's length. This ensures that the loop runs to the end of the list. For a given bounding box, the current iteration value is used as an index to retrieve label and score values. After printing these values, the console is displayed. The code displays the label and score for each bounding box in a list, showing the results of object detection with YOLOv3 and Keras. This first line retrieves the coordinates of a specific box from the list of bounding boxes, indicated by I. A next line assigns y1, x1, y2, and x2 with the ymin, xmin, ymax, and xmax coordinates. In this case, these coordinates represent the box's top left and bottom right corners. A box's width and height are calculated by subtracting its x1 coordinate from its x2 coordinate and its y1 coordinate from its y2 coordinate. Based on the coordinates and calculated values, a rectangle object is created. The variable rect contains this object. Last but not least, the addPatch function is used to add the rectangle to the plot, specifies the width, height, and color of the plot box. Finally, this code snippet uses YOLOv3 to retrieve, calculate, and draw bounding boxes for object detection in Keras. The code produces YOLOv3 labels and scores for objects detected by Keras. The top left corner of the image is filled with text and scores in the pyplot text function after the objects are detected. This variable combines the label name with the corresponding score, which is displayed in object name score format. In the text, the variables x1 and y1 determine the x and y coordinates, and white is the color. As a result, the objects in the image can be identified and tracked easily. The following code snippet is part of a larger script that uses the you-only-look-once YOLO algorithm to detect objects in images. This part of the code shows boxes around detected objects with corresponding labels and confidence scores. In order to implement the drawBoxes function, we must define the following parameters: file name, the name of the image file; vboxes, a list of bounding box coordinates; vlabels, a list of labels for each detected object; and vscores, a list of confidence scores. A variable named data is created to store the image loaded with pyplot.imread. After that, the image is plotted using the pyplot.mshow function. Using the pyplot.gca function, the context for drawing boxes is obtained and stored in a variable called ax. A context will be used to draw boxes and text on top of the image. Afterwards, vboxes coordinates are looped through, as per the bounding box coordinate list. Each box's coordinates are extracted and stored in separate variables: ymin, xmin, ymax, xmax. An area within the bounding box has the following coordinates: top left, bottom right. Following the calculations using these coordinates, the box's width and height are calculated. Using the parameters provided in this information, a rectangle is constructed using the rectangle function. With the help of ax.addPatch, this rectangle is added to the context. Each box's label and confidence score are then calculated and displayed in the top left corner. Last but not least, the pyplot.text function, which draws the labels and scores directly over the image, is used to draw them. Pyplot.show displays the plot once the boxes have been drawn and the text has been added. A code snippet like this will draw boxes around detected objects and display their labels and confidence scores over the image. The code snippet uses Keras's YOLOv3 model to detect objects in a photo. First, the function call drawBoxesPhoto file name, vBoxes, vLabels, vScores, calls the function drawBoxes and passes 4 arguments to it: the file name of the photo, a list of bounding boxes, a list of labels, and a list of confidence scores. After that, drawBoxes calculates the coordinates of each bounding box in the list based on the photo's size. Additionally, it draws the bounding box label and score using OpenCV on the photo. For all bounding boxes in the list, this process is repeated, resulting in a photo with all detected objects highlighted and labeled. A photo is visually analyzed in this code using the YOLOv3 model to detect objects and display them.